This is DS1 from ECB section. My roll number is 234090495. My topic is derived bandwidth of an RLC circuit. Introduction to RLC series circuit or electrical circuit that contain a resistor or an inductor L and a capacitor C connected in series. These components work together to create complex electrical behavior, making RLC circuit useful for a variety of applications. Defining bandwidth in RLC series circuit. Frequency response. The bandwidth of an RLC series circuit is the range of frequencies over which the circuit's output amplitude remains within a specified percentage of maximum value, typically 3 dB or 70.77% of the peak. Transfer function. The bandwidth is directly related to circuit's transfer function, which describes how the output signal is affected by the input across a range of frequencies. Quality factor. The bandwidth is inversely proportional to the circuit's quality factor Q, which measures the selectivity or sharpness of the circuit's frequency response. Relation between resistance, inductance, and capacitance. In an RLC series circuit, the resistance or inductance L and capacitance C work and together to determine the overall behavior of circuit. The interplay between these three components is crucial in defining the bandwidth of the system. The resistance affects the overall current flow. The inductance influences the circuit's ability to store and release energy, and the capacitance determines the circuit's capacity to store release electric charge. The combination of these elements dictates the frequency response and the bandwidth of RLC series circuit. Derivation of bandwidth formula. Step 1. The bandwidth of an RLC series circuit is determined by the relation between resistance, inductance, and capacitance of the circuit. Step 3. Step 2. The resonant frequency F0 of the circuit is calculated as 1 by 2 pi root of LC. Step 3. The bandwidth is defined as the frequency range between 2 points where the power is half the maximum value or minus 3 dB points. Bandwidth calculation for a series or circuit. As we know, IRMS equal to gamma divided by Z at resonance Z equal to R. IM equal to RMS divided by R. When P equal to PM by 2, IRMS equal to IM divided by root 2. Rho RMS divided by Z equal to rho RMS divided by root 2 R. Therefore, Z equal to root 2 R. Z equal to root of R square plus X square equal to root 2 R. At half power frequency X equal to plus or minus R. Omega L minus 1 by omega equal to plus or minus R for omega 1 and omega 2. At omega 1, omega L minus 1 by omega C equal to minus R. Omega 1 equal to minus R divided by ZL plus root of R square divided by 4R plus 1 by LC. And at omega 2, omega L minus 1 by omega C equal to plus R. Omega 2 equal to R divided by 2L plus root of R square plus 4L square plus 1 by LC. Thus, bandwidth of circuit in delta omega equal to omega 2 minus omega 1. Therefore, delta omega equal to R by L. Factors affecting bandwidth in RLC circuit. Resistance or higher resistance in the circuit reduces the overall bandwidth as it dampens the circuit ability to respond to rapid changes in the input signal. Inductance. Increased inductance leads to a narrow bandwidth as the inductor's reactance limit the higher frequency response of the circuit. Capacitance. Larger capacitance value results in a wider bandwidth, as the capacitor's reactance allow for better high-frequency signal transmission. Frequency: the operating system frequency of the circuit also affects the bandwidth, with higher frequencies generally allowing for wider bandwidths. Importance of bandwidth in circuit designing. Bandwidth is a critical parameter in circuit design, as it determines the range of frequencies that can be effectively transmitted or processed by the circuit. Proper bandwidth management is essential for ensuring optimal performance and preventing signal distortion or loss. Bandwidth constraints can impact the speed, fidelity, and functionality of electronic devices, making it crucial consideration in the design of amplifiers, filters, communication systems, and other electronic circuits. Practical application of bandwidth in electronics. Radio communication. Bandwidth is critical for transmitting high quality audio and video signals in radio, TV, and wireless communication systems. Audio applications. Sufficient bandwidth is required for high fidelity sound reproduction in music plates, speakers, audio amplifiers to preserve the full frequency range. Digital data transmission. Bandwidth limitations impact the maximum data rate and throughout in internet, computer networking, and digital communication technologies. Limitations and considerations in bandwidth calculations. Influence of components tolerance. Parasitic effects, nonlinear components, frequency dependence. Comparison of bandwidth in different circuit configuration. The bandwidth of an RL circuit can vary significantly depending on the specific circuit configuration. Comparing the bandwidth of different configuration provides valuable insights for circuit designing and optimization. 20K Hz bandwidth of RL circuit with low resistance. 10K Hz bandwidth of RL circuit with moderate resistance. 5K Hz bandwidth of RL circuit with higher resistance. As the resistance in circuit increases, the bandwidth decreases. This is because higher resistance dampens the oscillations and reduces the frequency range over the which the circuit can effectively operate. Understanding this relationship is crucial when designing filters, amplifiers, and other circuits where bandwidth is a key performance metric. Conclusion and key takeaways. Bandwidth importance factors to consider practical applications. Thank you.